Hello everyone, my name is Rafał Majcher and I would like to invite you to the world of the automotive cybersecurity. This is the IT/OT Cybersecurity Conference, so this presentation was prepared with an assumption that most of you are the experts in the cybersecurity area, but it may be a case that you never worked within the automotive industry and especially within the automotive product cybersecurity. So a few words about our small company. The company was founded in 2021. The company is located in Krakow in Poland. For those of you who come from the abroad, it's just a city located 80 kilometers from here, the second biggest city in Poland. We perform the automotive engineering services in the area of the cybersecurity, systems engineering, software engineering, software systems test, project management, and also the others. And I am the chairman of the board. A few words about myself. So the case is that I'm working within the automotive engineering since almost 13 years. I was starting within the test department. I was working as the software systems test engineer for quite a small components of the car, for example, the alarm sirens that are prepared just during a few months of time with the usage of the few engineers. And I was moved to the systems engineering department. And we were working on the BCMs, the body controller modules, which are the heart of the entire centralized architecture of the car, and the ECUs that are something like 300 inputs and outputs, and are described with the usage of over 100,000 system requirements. Yeah? And then I moved to one of the OEMs, and I was working on the all-wheel drive controllers. I moved back to the tier one, and I started to working on the ADAS projects on the front camera as a manager of quite a big software team, over 100 software developers, software architects, software project managers, and so on, in a huge ADAS front camera project that was presented on the Customer Electronics Show in Las Vegas. So a quite innovative and new system. I'm the Master of Science in Electronics in the telecommunications engineering area. And the case is that, of course, we are working for multiple companies, and we cannot present here anything that is, under the intellectual property of those companies. So we'll be, just speaking. I will be speaking about some generic topics. Before we will move into the automotive cybersecurity, just a few words about the automotive world in general. So the first thing you need to know about the automotive is that the cars are manufactured by the OEMs. And the OEMs are quite a big companies, but the OEM is not manufacturing the entire car fully on his own. Yeah? The case is that the car is built with the usage of the components, for example, the ECUs, yeah, which are created by the tier ones, and those are also the big companies. When I say the big company, I think about a company like over 100,000 employees all over the world. Yeah? And the case is that those ECUs, of course, not built in total by the tier ones. Those are built with the usage of the subcomponents, for example, microcontrollers, software components, and so on, that are created by the tier twos. The case is that it is creating quite a complex supply chain, and of course, the cybersecurity needs to be assured and cascaded down through the entire supply chain. I was speaking about the ECU. Perhaps a few words what is the ECU in general. So the electronic control unit, it has some supply lines, the VBAT and the ground. It may have some sensors. It may control some actuators. And it for sure has some communication buses to communicate with the other parts of the car. Inside the ECU, you have usually one or more microcontrollers, which has its CPU, and the volatile memories and the non-volatile memories with the program and the data. Of course, there are some input and output circuits, power supply circuits, communication buses, and so on and so on. In general, this is how it looks like, yeah? So one more time. This is the embedded system in the automotive electronics that controls one or more of the electrical systems or subsystems of the car. The very important thing is that it is a safety critical system, so if something will go wrong, multiple people may die, and we have a big diversity of, let's say, size of those systems. You have a very small systems like the alarm sirens, like, 3 wires, and just it is playing, the sound or not. Or you have, for example, the body controller modules, ECUs, which has 300 inputs and outputs, multiple communication buses, and so on. The key component of such an ECU is, of course, nowadays in software. In general, the automotive is the ultimate kingdom of the language C and also C++, but the Rust is incoming, and it is something that maybe one of the future solutions here. When it comes to the operating systems, the case is that this is what is the most popular here in the automotive is the AUTOSAR Classic or AUTOSAR Adaptive. There are also multiple proprietary tier 1 or OEM solutions, and there are, of course, also the rich open operating systems, like, for example, the QNX and so on. So we have a huge diversity of those, yeah? And you need to be aware that we have multiple ECUs in a car, usually over 100, sometimes 150, and so on. Those ECUs are being created by multiple different companies, with the use of the multiple different components, and at the end, it all needs to be cyber-secured properly. The example of the ECUs you have here listed, like, for example, the engine control module, on the transmission control module, the simple door control units, or, for example, the telematics or the BMSs. How, in general, those ECUs in the car are connected is described in this in those slides. The case is that we are starting with some, solutions that were used rather in the past. So the case is that we have, multiple ECUs here connected over the CAN or LIN buses, and with the data processed inside those ECUs only, and we have somewhere here the gateway that is, simply forwarding the necessary traffic between those CAN and LIN buses. Yeah. So the case is that buses were grouped in the domain, and those were the specific ECUs there. The case is that the communication buses that were being used was especially the CAN in its high speed 500 kilobits per second option, or low speed, the fault tolerant 125 LINs, but also later on FlexRays and the CAN FDs. The most important thing, the entire logic is within the ECU gateway is only, gating the data. The issue with this solution, with this architecture, is that the entire length of the cables of the wiring harness in cars is an enormous one, yeah? Because you need to connect multiple ECUs that are, for example, in the body domain, and they are located in physical different locations of the car. And it is an issue because in the automotive, in general, we would like to decrease the size of those wires, to decrease its cost, to decrease its weight, and weight is, of course, associated to the emissions, yes, so the CO2 emissions and so on. The case is that the current solutions went towards the domain architectures when the significant part of the data processing was moved from the ECUs to the domain controllers. The case is we have the Automotive Ethernet as the backbone here, with those domain controllers connected over with the usage of the switch. The case is that we have here introduced the Automotive Ethernet buses. Those are usually those with the T1 in name, so multi-giga base T1, 1000 base T1, 100 base T1, and so on. Yeah? And this is how it looks in the car. Unfortunately, the issue is that the length of the wiring harness in the car is still quite a long one. And the case is that this is what comes in here are the future solutions, which is called the zonal architecture. And perhaps I will move to the next slide. Take a look. Everything is more or less connected based on its physical location. So as a result, the case is that you have, for example, front-right zone controller that has a very short wirings to the nearby ECUs, but to be able to create this type of the architecture, you need to create those zone controls which are cross domains, yeah, which are handling multiple different features of the car. And of course, also in this situation, a lot of the data processing is moved to the central computer, which is causing, from the cybersecurity point of view, some risks, unfortunately, yes? So the case is that we may have some nice features like the virtualizations of the ECUs containers, but what about, for example, the isolation of those containers, yes? the hypervisor within this central computer is, quite at quite a big load when it comes to its cybersecurity. Yeah, and we have also the determinism here required, and because those are the hard real-time constraints that needs to be met. Yeah, so the case is that this is how it is how it is moving, and what is the direction it is going towards. Yeah. When it comes to, in general, how the software is constructed within the car, the case is that this is what is the most popular, is the ASPICE 4.0 framework. It is defining what are the required steps and what are the required engineering work products to be prepared before we will actually write the source code. Yeah? So the case is that it starts with the requirements elicitation. The systems engineering are gathering the requirements, all the standards, required norms, and so on, the requirements from the customer, also the requirements from the manufacturing, the internal and the external stakeholders. They also are creating the system requirements and the system architectural design. The case is that later on, once the product is being prepared, there is the system test engineering area on the right, that is SYS5 and SYS4, that is performing the system verification and system integration verification. And at the bottom part of that, you have the software activities, so the software requirements, software architectural design, software detail design, and the unit construction. At the very bottom of that, there is, the software is being prepared. You have also the unit test here, the integration verification, and the software verification. All of that is linked. You have both the vertical and horizontal traceability, so you are able to see that a specific line of the source code was created as a result of a specific requirement. Yes, and when it comes to the cars, the amount of those lines of the source code is quite a big one. It is usually estimated at something like 100 million. Yeah, so it's quite a big. The other thing that impacts the cybersecurity is the average age of cars. I was just taking a look at some data from, for example, the CEPIC database and so on. It oscillates roughly around 15 years. Yeah? And what does it mean? And this is the average value. What does it mean? If someone just bought a brand new car, there must exist another person who has something like 30 years old car, or multiple people who has, for example, 20 years old car. Yeah? So please take a look. You manufacture the car, you need to assure its cybersecurity. You've taken the money once, yeah, and you need to update it for a very long time, yeah. Who is going to pay for that, yeah? So those were a few words about the automotive in general. So now we will move to the automotive cybersecurity, yeah. So the first thing we need to consider are the vehicle attack surfaces. There is a lot of those surfaces when it comes to the vehicle. We are starting with the things like the radar, lidar, and the camera sensors, to the vehicle to everything communication, like vehicle to infrastructure, vehicle to other vehicles, and so on. The case is that the cars are usually connected to the 4G, 5G networks. Yeah, there is the Bluetooth. There is also a wireless. We have, in the cars, the entire infotainment systems with, even, the DVD players, USB ports, and so when someone can, stick somewhere there, yeah. The case is that we have the OBD2 connector that someone can plug in and have the direct access to the communication buses. Of course, the GPS, the DAB radios, and so on. The cases that we have, of course, those passive keyless entry and the remote keyless entry and the key fobs, yes, so opening the car. We have, this is what is getting a lot of importance nowadays, the charging, yeah, and of course the wireless tire pressure monitoring systems, yeah. The case is that's the car. There is also another side of the story, yes, because the car is connected to the OEM's backend. Everyone has a smartphone with the application that is able to control the car with the usage of, yeah. And the case is that this as well needs to be cybersecurity. So see here it comes, the IT cybersecurity. And of course, all of those components in the car are somewhere manufactured, and the car itself is somewhere manufactured, yes? So the car may be, even attacked at this stage when it is, still being manufactured at the tier 1, tier 2, or the OEM manufacturings. And the case is that world is, changing in a quite a rapid way, And there are, multiple new ways of attacking the car that didn't exist something like 10 years ago. Yes, so think, for example, about the drones carrying the Wi-Fi dongles that are trying to get into your car with the usage of those. Or, for example, that someone can just come and, if your car is open, plug into the OBD port, a device that will silently transmit, all of the data and so on. Or just, plug something into the USB port, yes? So in general, the main question is, how do we know what and how to protect? Yeah? Of course, we know that everything that comes from the internet side needs to be taken on a priority because it scales up very easily. Yeah? If you will attack the OEM's backend, you may gain control not over just one single car, but over 100,000 of cars. Yeah? But is it sufficient? Yeah? So I will give you an example. The car theft issue. How many of you know a person that had their car stolen? I guess not so many. Yeah? So I just digged for some data. Country one is Poland. Yeah? And roughly per year, there are 5,500 cars being stolen in Poland. Yeah? But unfortunately, in the other countries, this problem is much, much bigger. So there is another country not so far away from here, with the population 70 million, and 130,000 cars stolen per year. Yeah? How it is happening? Yeah? So just an example case. Yeah? The entire car was protected, and there are, some wiring harnesses there. Yes, and the thief is just, with the usage of some simple tools, just destroying the front bumper that is made with the usage of the plastic. And here we go. Here we have the access to the CAN pass directly in the car. Yes, simple tools that are, that piercing the isolation in those cables during just 2 seconds of time. And here we go. Yes. The other story, a very simple one. Because the case is that there are some rear doors here. Yes, the trunk. And the case is that there are some lights here, the rear cameras and the other stuff. So there are, some wires going there, yes? So in some of the cars, it is possible to just break the rear window to get an immediate access to those wires, yeah? Why the rear window? Because it's very easy and cheap to replace later on, yeah? Without, paying too much for, because once you stolen a car, you would like to, repair it, yes, and to sell it, as soon as possible. You don't want to destroy this car too much, yes? An interesting way, yeah? So how does it look like? Yes, this is the example from this second country, yes? Usually, within 4 hours, the car is in the container on a ship. And those are the data from the Interpol and the local police in that country, packing into the ship, or just cutting the car into the halves. Yeah, and you have 4 hours. If you didn't find your car within 4 hours, it's probably also completely lost. Yeah, and how it is possible that such things are happening? Yes. So, for example, some of the most typical attacks. Based on the direct connection to the internal CAN bus, for example, yes, those pictures I show you that someone, broke the window and so on, yes. So the threat actors are using some special custom devices, like, for example, the overpowered CAN transceiver. When the CAN was designed in the 1980s, no one was thinking about the cybersecurity of that so much. There were not so much the cybersecurity requirements. Why? Because think, how the world looked like in the 1980s, yes? How your smartphone looked like, how your internet looked like. Did you have a laptop even? Yeah? So it was not so easy, to get, some knowledge how to do that and so on. You were not able, to ask the AI, to get some help, how I can attack a particular car. Yes? So there were no such requirements for that. And this is currently being used by the threat actors, yeah? And if you are a master of science in electronics, you are able to construct such a device very easily, within just a few minutes of time, yes? Because if you are a threat actor and the attacker, you do not need to meet, all of those EMC standards and so on. You do need to follow the protocols, yes? You are going, to just create a device that will speak, to the other devices in a way those devices will trust, yeah? And you are able, with such the custom devices, you are able even, to overwrite what is written by the other devices, or you are able, for example, to use some features of the car, for example, to make the other devices silent, yes? Like, for example, to overload their counters of the errors and so on. Very easy, yeah? So that's the case. The other thing is that just direct connection through the OBD port inside the car. This is the other story, yes? So unfortunately, it is, coming with some consequences. Media interest, unhappy customers, problems with insurance companies. Some of the OEMs even reached such a state, that they were trying to sell the cars to the customers, and the insurance companies were saying, we are not insuring those cars. Yeah, quite a big problem. Yes, and of course the social effects, because those stolen cars are later used to commit some other crimes. Yeah. So, for example, what is being changed and what is other later on? For example, the tracking devices. Yeah, a very interesting story in that country. The police equipped 2,000 police cars with special devices that are able to receive the signals for those stolen cars. All of those cars have added some devices that in case the car is being stolen, it starts transmitting the data with the usage, what is interesting, VHF range of the frequencies that are harder to jam than the GPS and better propagate through buildings, through underground garages, containers, and so on. Yes. Also, all of the police helicopters are equipped with this system, and so on. With a simple triangulation, they are able to catch such a car before it will be put into the house. Yeah. Some solutions like, even, people are covering, the wires, with some, anti-cutting sleeves, adding some devices that will, just filter some of the CAN bus traffics and so on. That is causing some functional safety concerns. Yeah. Some people even cover their OBD connectors with the car with some, just pieces of the metal. That looks a little bit funny, yes, but what you may do in case if you know that your car, for example, is in the, let's say, top 3, for example, of the cars that are being stolen, yes. So it all has limited effectiveness, comes with an additional cost, increase the weight of the car, and so on. So the question is, perhaps it would be possible to protect that in a much better and effective way, for example, in the software. Yeah? But when it comes to the software, we need to be aware that there are some, let's say, types of the attack, like, for example, the fault injection ones, because, in a car we have a specific story, which usually do not have, for example, at the manufacturing site, yes? Everyone who has the access to the car is able to do everything with all of those components, yes? So it's able to perform, for example, the fault injections, which are getting its popularity, and those types are, for example, the electromagnetic fault injection, the power glitching, the clock glitching, the laser fault injection. Especially those power glitching ones are very simple because there are some, even articles in the internet you can Google for within 1 minute that you are, for example, you will be able to see how to power glitch some of the processors, and that you are able to do that within just tools worth 10 euros, yeah, and just soldering one additional power transistor, and that's it, yeah. And the entire procedure is already ready. So, for example, if you are later on preparing a documentation for such a car and creating a TARA, you cannot say that it is, a very sophisticated attack that only, a few people in the world can perform. Yes, because it can be done, by a kid. Yeah. So this is how it looks. Of course, you need to play a little bit about the time, duration, intensity, position parameters. The case is that the 3D printers are quite well used, to positions, for example, of those electromagnetic fault injection antennas and so on. Yeah. So this is something we need to be aware of. So the case is that what is helping us and what is making our life a little bit easier are multiple regulations, standards, and specifications. And the case is that the automotive cybersecurity, I think the first one which I was aware of that came and was designed especially how to protect the cars itself. In 2016, there was the SAJ 3061. It is already kind of the historical standard, but it was one of the first one that appeared in this area. In the 2021 January, the UN EC regulation came into play, and it is fully binding since 1st of July 2024. And this is something that is the law that needs to be followed. Yeah. So the case is that 54 countries who signed that in 2021 just stated, okay, If we are performing the vehicle type approvals, the other word for that is homologation of the car. In the past, there were, some braking systems and so on in scope of that. Since 1st of July 2024, the automotive cybersecurity is in scope of that, yes? And if you are a car manufacturer, the OEM, you need to perform two things, yeah? The first thing is the cybersecurity management system, which you need to prepare and certify. And the next thing, you need to perform the vehicle type approval for every type of the car you manufacture, yes? And to be able to do that, there is a lot of things you need to meet and take care about. It also includes the auto vehicle system, the IT systems that are connecting to the car. So that's the UNC regulation. 2021 July, the A-Spice for cybersecurity. So I was showing you the A-Spice in general. There is some addition, some extension to that called the A-Spice for cybersecurity 1.0. Not followed currently by many of the companies, but it may change, yeah? And in 2021 September, the ISO SA standard 21434 appeared, road vehicle cybersecurity engineering. There will be some more slides about that, yeah? The case is that there are also some norms for auditing the cybersecurity and so on, yes? This is what is interesting, is that it's not only, the European Union countries and the UNEC regulation countries that are doing that. For example, China has a very interesting GB 44495 regulation. It is in fact a kind of the national standard in China, but the law works in China in a little bit different than here. You need to by law to follow the standards when you are in China. Yeah, so its role is similar to our regulation, but it is even more demanding than the regulation we have here in Europe. Some additional activities needs to be performed on the top of that. Yes. And last year, recently, the new version of A-Spice Cybersecurity 2.0. There are some new incoming things that are going that are going to prepare and are being prepared at the moment. In the November last year, I was nominated by Poland to join the ISO community, so the International Standardization Organization, and I joined the works on to prepare the new version of the ISO SA 21434. I came, I think, recently on behalf of Poland with some 10 improvements areas, and I raised those, and I hope those will be included in the new version of the standard. Yes, there are two things other than the new version of the ISO SA 21434 being prepared at the moment: the CALs, cybersecurity assurance levels, and the targeted attack feasibilities. So it will be the PAS, so the publicly available specification, and the next thing, the verification and validation, which will be the technical report. Yeah. Okay, overview of the ISO SA 21434 and so on. The case is that there are multiple activities to be performed. There are some activities at the company level, like the cybersecurity governance, trainings, and so on, culture, yes, information sharing, management systems, tool management, and so on, audits. There are some project-dependent activities, yes, like for example, okay, we need to be sure that we know what are the cybersecurity responsibilities with the project. We need to prepare the cybersecurity plan. We may tailor out some of the activities we don't want to prepare if we have a good rationale for that. We may reuse some of the devices together with its cybersecurity solutions and documentation and so on. We need to prepare the cybersecurity case. In some cases, also the cybersecurity assessment and so on. The case is that, of course, there are also some distributed cybersecurity activities, like, for example, the assessment of the supplier capability. So if, for example, the car manufacturer is nominating a particular tier 1 to create a particular ECU, this OEM may ask, okay, guys, what is your maturity in this area? How you can prove that you are able and capable to be able to follow all of that, yes? There are some continual cybersecurity activities like the cybersecurity monitoring, vulnerability analysis, vulnerability management, and so on. And when it comes to the main activities within the project, we are starting with the concept phase. We are preparing our item definition. Then we are creating our TARA that is described at the bottom of that. We are creating our cybersecurity goals, the generic cybersecurity concept. And at least in theory, this concept phase should end before even writing the first line of the source code within your solution. Of course, the reality is not so bright. Yes, it is sometimes it is the case that it is just created in a retrospective way. Yeah, But then you move to your product development phase. You're designing the solution, performing the verification, validation, and this is what may be interesting, here on this IT/OT cybersecurity conference, the production area. So this ISO 21434 is also coming with some requirements that the production needs to be handled in the proper way, and the production control plan needs to be prepared that is taking into account how all of the cybersecurity requirements for the manufacturing that were prepared during the design of the ECUs are later followed. Yeah. So this is more or less how it looks like. Yeah. The case is that at the beginning of the project, we are performing the cybersecurity relevance decision if our issue is even in the scope of that. We have the ASILs, PIAs, communication bases, other criteria, and so on. We are creating the cybersecurity phase agreement that is describing who is preparing what. We are preparing the cybersecurity plan, and we are starting with the concept phase. We are starting with the item definition, so what is our boundaries, interfaces, operational environment, and so on. This is, a very important step, because without that, it is very hard to create the TARA. And then we are moving to our TARA, threat analysis and risk assessment. We are just thinking about, okay, what are our assets? What do we need to protect? Yeah. What are the cybersecurity properties of those assets we need to protect? The case is that we are creating the damage scenarios. So high level, road user level, negative consequences, what may go wrong, yes? And what kind of harm may be as a result of that. Then we have, some impact ratings in case of the safety, financial, operational, privacy. And we have those impact ratings here. We are moving to another path that is, definition of the threat scenarios. Yeah. So we are asking a question, okay, how exactly such an attack we are considering can be performed? Like, for example, spoofing CAN message for the braking ECU leads to loss of integrity of CAN messages, and there be loss of integrity of the braking function. Yes. Then we are moving to the attack paths. Okay, so we are asking ourselves a question. Okay, in details, how to do that? Yeah, in our car, in our infrastructure we have, and so on. Yes. Based on that, we are calculating some attack feasibility ratings. Yeah. Of course, those depend how much time we have, how much knowledge is required to perform the attack, and so on. And based on all of that, we are calculating the risk. What is the risk associated with a particular threat? Yeah. And based on that, we are performing the risk treatment decision. What we are going to do with that? Are we reducing the risk with, for example, using some cybersecurity controls and so on? Or perhaps we are accepting the risk. We are thinking, okay, in this case, the risk is low enough, so we can accept that. Or we are buying an insurance, or we are avoiding the risk. That's an interesting point. We may think that this is our feature in the car is, for example, too dangerous to implement that, because we know that, for example, it will be not so easy to efficiently cybersecure that. So we may even go towards avoiding the risk by stopping the activity that caused the risk. Yeah? Then we are creating the cybersecurity concept, and so on. So a few examples of the cybersecurity controls. Yeah? We are using to secure the in-vehicle part of the car. We have the HSM modules, one-time programmable memories, security logs, security onboard communications. We are encrypting the external memories, implementing some stack smashing protections. We are disabling the debug interfaces like the DAP, JTAG, XTP, and so on. We have the secure diagnostic feature. All of the ECUs have some, for example, UDS diagnostic protocols, and to access some more interesting features, you need to be authorized to do that. So there are two ways of the secure diagnostics. We have also the secure flashing. We have some network-based IDS, IPSs inside the car. We also have the MACsec, IPsec. The things like the heartbeats, conformal coatings, even obfuscation of the hardware, and so on and so on. There is many of those. Not enough time to describe. The case is that an interesting thing is, for example, the SHI, so your hardware extension. It comes, with an idea that it's not so easy to cybersecure the software itself. It's a good thing to utilize some hardware solutions for that. The main concept behind SHI is that when you have some, for example, cryptographic values, the cryptographic keys, you're not storing it within your main software. You are passing that into the dedicated hardware within your microcontroller. And the case is that it is constructed, the microcontroller is constructed in such a way that those keys can never leave it, yeah? So the main CPU and its software is speaking, hey, she, please perform, for example, encryption of this data with the usage of the key number 5, yeah? And she is returning back. It's a very simple solution, a simple state machine with some accelerators, yeah? The case is that we have also the HSMs, the hardware security modules, that there are different types of those, and starting from the light Evita ones that are quite similar to the SHI, to the medium and full Evita ones. The main difference between those is the present of the, here at the bottom, you have the secure CPU, yes? So this on the right is just a simple state machine, and those on the left has its dedicated software, yeah? And you can create anything out of that. We have, for example, secure onboard communication, and this is an interesting thing because on all of those communication buses within the car, in most of the cases, we are not ciphering and we are not performing the encryption of the traffic. We are only signing the messages, so we are assuring its authenticity. Yeah, only some parts of the communication, like for example, delivery, of the cryptographic material of the keys and so on. This is something that is encrypted, but 99% of the traffic inside car, you can read it, easily. Yeah. But if you would like to verify if it is, a valid message, the case is that you need to have the secret key shared with you. Yeah? So that's the case. The case is that multiple algorithms currently in use. Of course, we are quite aware about this quantum computing challenge that is in front of us, and especially because of the fact that we are going to create our systems for many, many, many years. Yeah? So this post-quantum cryptography epoch is incoming, and as you saw in the previous slide, the case is that it's a typical situation that once you manufactured your car will be alive for 20 or 30 years. If you will take a look at this date, when those quantum computers are expected, it's just in a few years. Yeah? So your cars will face that epoch. Yeah? And many companies are currently, thinking about how to deal with that and so on. There is an idea, for example, of the crypto agility, because all of those algorithms were quite recently prepared, and it is, it may be a case that some of those will be broken. Yeah, and what to do that? In case if you already manufactured, for example, hardware that has the hardware accelerators that are working only with those algorithms, yeah? So there is an idea of this crypto agility to just prepare the solutions in such a way that we will be prepared for the future changes of those algorithms, yeah? Because we need to take into account the fact that some of those may be broken in the future, yeah? So that's the case. We have also some multiple other challenges we are facing. So, for example, the generative AI, yes, the attackers will for sure use that, yes. So the case is that why should we be behind? Yeah, we should also use those to perhaps speed up our activities, yes. But there comes some big problems and issues, for example, about the privacy, yes. If you will start preparing your Tara for your vehicle with the usage of the ChatGPT, of course, ChatGPT is storing all of the data you ever provided, yeah? So some other people will just ask the questions, okay, this type of the car, what are, for example, the risks that were accepted, yes? What were the attack paths that were not protected, anyhow? What are the cybersecurity controls implemented? What are not implemented in that car, and so on? So the case is that it is quite a challenging thing how to use those tools to not violate, this confidentiality of the information, intellectual property, and the privacy of that. Yeah, the increase of the technical complexity of the cars. This is also a big problem because it's very hard to cybersecure something that is very, very complex. And I already said before, 100 million lines of the source code written by multiple different dozens of companies. Yeah, in the different parts of the supply chain, it's an issue. Yeah. Different standardized regulations in different countries and so on, convergence, or perhaps something completely different, divergence, yeah? Different rules in China, different rules in Europe, yeah? What in case if the vulnerabilities will be found in your hardware, yeah? If you will, for example, use the HSM and it will be discovered as the vulnerable in the future, yes? you will manufacture 1 million of the cars. Will you perform the recall and exchange all of this hardware in all of those 1 million cars, and who is going to pay for that? Quite a big topic, yes. The case is that increased memory consumption, PQC and so on, and of course the effective cybersecurity testing, how to do that and so on in a short time with the limited funds and so on. Yeah. The case is that also those new architecture that were ingoing comes also with the high complexity of this central computer. Yeah. And the case is that we need to think about the new cybersecurity controls, like for example, isolation based on the hypervisor only, or perhaps supported with some in-chip firewalls and so on and so on. Yes? So the case is that this area of the knowledge and the engineering is, really growing and is facing an enormous challenges nowadays. Yeah. So I would like to thank you for the presentation. That's all for today. Do you have any questions? No questions. Okay, then thank you very much. Have a good day.
Bardzo dziękujemy za prezentację.